A distributed system is a group of autonomous computers that work together to appear as a single system to the user. These machines may live in different physical locations, but they communicate and coordinate through a network to share resources, process data, and execute tasks. Distributed systems are designed to scale seamlessly and handle demands that a single machine simply cannot. They're the backbone behind platforms like Netflix, Google, and Amazon, ensuring that billions of users experience speed, availability, and consistency, often without even realizing the complexity behind it. We use distributed systems because the modern world demands more than one server can offer. Global applications must serve billions of users, process petabytes of data, and be always available. A single machine can't provide that. Distributed systems allow us to scale horizontally by adding machines, maintain uptime through redundancy, and deliver content faster by moving data closer to the user. From cloud infrastructure to real-time messaging apps, the digital services we rely on every day are powered by these complex but essential systems. Scalability is the system's ability to handle increased load, and fault tolerance is its ability to keep running even when parts of it fail. Distributed systems scale horizontally, meaning we add more machines to the system, not just upgrade a single one. They tolerate failures using redundancy, automatic failover, and health checks that reroute traffic when a component stops working. Together, scalability and fault tolerance make it possible to grow without interruption and recover without data loss, even in the face of real-world chaos. Reliability, availability, and consistency are pillars of distributed system design. Reliability is about whether the system performs correctly over time. Availability means the system is responsive when users need it. Consistency ensures that every user sees the same data, no matter which server responds. But balancing all three isn't always possible, and choosing which one to favor in different situations defines how your system behaves under load or failure. CAP theorem explains why it's impossible to guarantee consistency, availability, and partition tolerance all at the same time. In the event of a network partition, where some nodes can't talk to others, you must choose. Will your system remain available and serve possibly outdated data? Or will it ensure accuracy by rejecting requests until it's safe? That's the heart of the CAP trade-off. Systems like DynamoDB favor availability. Others, like traditional SQL databases, prioritize consistency. The decision defines your system's behavior in the real world. Partitioning, also called sharding, is how large databases are split into smaller, faster, manageable parts. Horizontal partitioning breaks rows into separate machines, while vertical partitioning splits columns. Hash partitioning evenly distributes records using a hashing function, and range partitioning organizes them by data ranges. A good partitioning strategy avoids bottlenecks, reduces latency, and lets your system grow without hitting a wall. Replication is about copying data to multiple machines to make it durable and fault-tolerant. In synchronous replication, all nodes must confirm a write before it's accepted. In asynchronous replication, data is written to one node first and then copied to others, often faster but with risk of temporary inconsistency. Quorum-based systems use read and write thresholds to ensure data accuracy, even if some replicas are unavailable. It's a powerful balance of speed, safety, and flexibility. Consistency models define how and when updates become visible across the system. Strong consistency guarantees that once a write is complete, every RAID will return the latest value. Eventual consistency allows for short-term divergence, with the promise that all nodes will eventually sync. Causal consistency tracks which updates are related and preserves their order. Choosing a consistency model means deciding how much freshness, speed and complexity your users and your app can handle. Distributed systems don't share a global clock, so they must find other ways to understand time and order. Logical clocks, like Lamport timestamps, allow systems to infer what happened before what. Vector clocks go further by tracking causality across multiple nodes. These tools are crucial in scenarios where ordering matters, chat messages, banking transactions, or collaborative editing. Without proper event ordering, systems risk corruption, duplication, or strange bugs. Concurrency control ensures that multiple users or processes can access shared resources without causing conflict. In distributed systems, this is even harder because operations happen in parallel across machines. Optimistic concurrency assumes few conflicts and resolves them after they occur. Pessimistic control locks resources ahead of time to prevent problems. Techniques like versioning, timestamps, and multi-version concurrency control help keep data safe, even in high-traffic, real-time environments. Nodes in a distributed system must talk to each other, often constantly. Communication happens through REST APIs, remote procedure calls, or messaging systems like Kafka or RabbitMQ. gRPC enables fast, binary communication between services. Message queues allow asynchronous interaction, which decouples services and improves scalability. The choice of communication method affects performance, latency, and system reliability, making it a critical design decision. Consensus is the process of getting all nodes to agree on something, like who the leader is or what value to store. This is difficult when nodes can fail or go offline. Algorithms like Paxos and Raft make it possible by requiring a majority to agree before changes are accepted. Coordination tools like Zookeeper and etc. implement these protocols and offer features like leader election and distributed locks. Without consensus, a system risks split-brain behavior and data inconsistency. Distributed transactions involve coordinating actions across multiple systems, like charging a card and updating inventory. Traditional two-phase commit protocols can do this, but are often slow and prone to locking issues. Modern systems use patterns like sagas, which break transactions into smaller local steps and provide compensating actions if something goes wrong. These approaches offer flexibility, better performance, and higher system availability under failure. Designing a robust distributed system means applying time-tested principles. Loose coupling keeps components independent, while high cohesion ensures related functions stay together. Stateless services scale better. Idempotent operations make retries safe. Use fail-fast logic to detect issues early in circuit breakers to isolate failing components. Asynchronous processing and retries with backoff can absorb transient errors. These principles help systems grow and evolve without becoming fragile. A service mesh is a dedicated layer for managing communication between microservices. It provides observability, retries, traffic shaping, encryption, and policies without changing your code. Tools like Istio and Linked add sidecar proxies to each service, intercepting and managing requests transparently. Combined with logging, metrics, and tracing, a service mesh gives developers control and insight into even the most complex architectures. Security in distributed systems must be built from the ground up. Use TLS to encrypt data in transit. Authenticate services with tokens or mutual TLS. Apply the principle of least privilege to restrict access. Secure your APIs, validate inputs, and monitor for anomalies. Distributed systems increase the attack surface, so security has to be layered, proactive, and continuously verified. Choosing the right storage and caching layer depends on how your system reads and writes data. Distributed databases like Cassandra or CockroachDB provide high availability and scale. Object stores like S3 handle unstructured data. And in-memory caches like Redis reduce latency for frequently accessed information. Mixing and matching these layers lets you optimize for speed, durability, and cost, but only if you understand the trade-offs. Failures happen, but a well-designed system recovers quickly. Health checks and heartbeats detect issues. Load balancers and service registries reroute traffic. Tools like Kubernetes can reschedule failed containers. And auto-scaling groups restore capacity. Recovery isn't just about restarting, it's about continuing to deliver service while degraded. Expect failure, design for it, survive it. Observability means knowing what your system is doing at any moment. Metrics track performance, logs record history. Traces show how requests move across services. Tools like Prometheus, Grafana, Elk Stack, and Jaeger make this possible. Without observability, you're flying blind. With it, you can detect, diagnose, and respond before users notice anything's wrong. The biggest mistakes in distributed systems come from assuming the network is perfect. That it's fast, reliable, secure. But it's not. The classic fallacies of distributed computing include zero latency, infinite bandwidth, static topology, and one administrator. These assumptions don't hold in the real world. Ignoring them leads to fragile systems that fail in unexpected ways. Real-world systems are built with all of this in mind. Netflix uses edge caching, chaos testing, and adaptive streaming to serve billions. Amazon shards inventory across regions for speed and resilience. Google Spanner uses atomic clocks and GPS to keep distributed databases globally consistent. These companies face the hardest challenges in computing and solve them using distributed systems. Distributed systems are powerful but complex. To design them well, you need to understand trade-offs, failure modes, and coordination patterns. Keep learning, keep experimenting, and keep asking, how do we build systems that don't just scale, but thrive under pressure? Because the future of computing is distributed, and it's already here.